So I think that's the relevance to this conference. I just want to tailor what I'm going to say. So I just want to get a show of hands. Can you put your hand up if you're a developer or an engineer? Okay. So I think we have it's about a 50-50 crowd. So this talk is normally geared a little more towards the technical. What I'll do is I'll try to just balance it around a little bit just to cater to the audience. So we're going to do two things here. First of all, we're going to talk about the theory of caching. So I'm going to give you some tips from the trenches, my 13 years of doing this, and it'll sort of set the theoretical context for then what we then go to standardize in the standard. So everybody kind of, I think, knows what a cache is. It's a high-speed location that you store data in that you think you're going to need again. And the benefit is, because it's in a very high-speed location, it speeds your system up because it's much quicker to get it that second time. So there's a couple of other implications that flow from doing that. So obviously performance is a really important one. But there's some other good stuff that happens. So given that a hit to a cache is incredibly low cost because you're just hitting RAM, you can actually, it's a way to actually vertically scale your system. So use the thing that was expensive. It can be a variety of things. Most commonly in business systems, it's a database. It can be as expensive as a mainframe hit. So it actually reduces the cost of your system and also gives you a way for the architecture to grow. Generally speaking, for a lot of enterprise systems, if you add caching, there's a certain finite scaling factor they have to get to, and often for the lifetime of the system, you're actually done. With web scale systems, that's not true. You have to keep scaling to infinity. That's not the case for most enterprise systems. Caching, when it's applied to one single computer, gives you scale-up capabilities. When it's applied to a cluster of computers, most of the vendors out here have the scale-out kind, which then allows you to actually both scale up and scale out. And the other thing is, because it's so cheap to hit RAM, these things can actually handle extreme bursts in load. So I think Black Friday, I think other events, sudden increases in load that would sink a standard system. So caching's a cool thing. And it's, if you can't really find a web scale architecture that doesn't have a caching layer built in. You should only use a cache when you can use the data more than once. Otherwise, there's no point. Seems like an obvious statement, but it's an important one to make. The other thing, obviously, caches have got to be really fast. If it's slower to go to the cache than it is the other system, you've got a problem. Couple of common problem areas for enterprise systems. The main one that people focus on is the database, but actually NoSQL itself is actually generally quite slow. So you can be in the range of 10 milliseconds to load a single row from a database or from a NoSQL system. Then there's anything web scale where you've got huge load, and then the other thing is, if you have to go across the network, you've got to go across the network, you really should think about caching. So an extreme case would be using Amadeus from across the world, something I had to do. But anything that's a SOAP call or a REST call or whatever. In terms of how things look, how caching looks, we'll use a data store as an example. What will happen is that you'll have a request that will come in. It'll go to the database. It'll get responded. On the way back, before the data is returned back to the caller, it gets put in the cache. Now, the next time a request comes in, it's in the cache. This is how the concept works. Now, I said before that it's pointless using caching if the cache is not super fast. Now, the fastest thing out there is registers, but there's not many of those. And then you've got L1 and L2 cache, but that's not very big. So practically speaking, we're talking about RAM. So RAM is the first place that we look to store data. Once we move off RAM, there is flash or SSD. And there's another thing that you're hearing a lot about at this conference, which is NVRAM. So if we take those as a, so they have, they're not as fast as RAM. NVRAM lies in between. Then SSD is slower again. But you can build up tiers like a pyramid with your fastest, most expensive in RAM, then going down to maybe NVRAM and SSD. Interestingly, as soon as, so pretty much all of the in-memory data grids are Java-based with one or two exceptions. When you're storing data in RAM in Java, there's a choice to be made. The choice is between storing the object ready to go for use by a Java program, which is called on heap, and it's in object mode. And the other one is to actually serialize it into bytes and then store the bytes. Now, if you want to use the data, you've got to grab the bytes, convert it back into an object, and work on it. So that's an extra step. Now, it's only RAM and heap RAM in Java where you can store an object. For everything else, you've actually got the serialization, deserialization overhead, which is quite significant. Then the next thing so eventually you'll exhaust the resources of one machine. For redundancy, you generally want to have a distributed cache that's got at least two anyway, but then to scale out, you'll keep growing. So what you then do is you do the same thing. You do this little orange pyramid, you do it across the network. So RAM across the network. Now, you might say to yourself, oh, well, why wouldn't you just, if you run out of space, why don't you just use disk on the same box? Well, actually, RAM across the network is way faster than disk. So for example, in Hazelcast, to go across the network and back on 1 gig is 140 microseconds. On 10 gig or 40 gig, it's 70 microseconds, versus with a disk, a spinning disk, you could be, you're going to be into milliseconds to actually access. So you've got a 3 order of magnitude speed difference between RAM across the network and local rotational disk. So these are the building blocks, and the new one in town is NVRAM. Now, NVRAM is random access, so it can be used as a block device or as random access. The way I'm depicting it here is as a block device. Another thing about performance is that oftentimes, if people are not careful and rigorous when it comes to performance, they'll spend their energy in the wrong area. So people tend to use the hammer they hold in their hand. It's important when you're looking at performance, and you usually are bringing caching in to solve a performance problem, to actually look at where you should spend your time. So you can apply Amdahl's law. You break your response time into segments, and then you say to yourself, okay, if I double the speed of that one part, how much does that affect the entire performance? So it stands to reason, if you spend a lot of time, Java programmers, for example, they tend to spend a lot of time optimizing some Java code. It might make a couple of nanoseconds difference, whereas if you're avoiding a network call, it's 10 milliseconds, so 5 orders of magnitude. So you've got to work in the right place. Another thing, once you get into caches, you should look at cache efficiency. So that is what percentage of the requests are satisfied by the cache. Now, we're looking for high cache efficiencies here. If you get those high efficiencies, it drives all the benefits of caching. A couple of tips of really good things to stick in caches that should generate this happy world outcome is reference data. So data that does not change within the lifetime of the application. I generally put all of that stuff in cache. The other thing is we want the data to be requested more than once. So if something's only valid for a couple of seconds, not a good candidate. So you put long-lived things in. The other thing is, how often is the data changing? If it's changing frequently, it has a short lifetime, so the odds of actually hitting it again are low. Now, in the past, when we were talking about 32-bit systems and small amounts of RAM, you had to be very, very cautious about what you stuck in cache. You couldn't stick that much in. That's no longer the case. With off-heap memory techniques and distributed caches, you can actually now go all the way to the extreme of putting the entire data set in cache. There was a gentleman came to the booth before, and he does that. he puts his entire data set in cache. And obviously, if you've got the whole data set in cache, you're not going to have too many hits that are actually missing the cache. So caching is, generally a really good technique. There are some problems that come in with caching. The first one, and this is a journey that pretty much every engineer has gone through that's used caches. You start off using caches. Generally the way it starts is you'll use what's called an in-process cache. So that's where you have an in-RAM cache on one physical server. What happens is you measure your cache efficiencies and everything's great. But actual production systems don't work this way. Production systems have multiple app servers, and what will happen is that the caching that's going on is only for that one, so not the rest of them. So what happens is as you go to n servers, then you end up requesting the data n times within the lifetime of that data. So you can have, this is a real gotcha. You start off with an in-process cache, everything's great, and then you start expanding, and before you know it, you're melting down your backing systems. The solution to this is a distributed cache. This is how people end up with distributed caches. So with a distributed cache, the request is made once, and then everybody's got it. Next thing is, with a cache, you've now got the data in two places. You've got your system of record, whether that's a NoSQL or a database. And then you've got a copy. Now, there's all sorts of problems that happen. It could be that you've got multiple applications connected to the database, and you've just got one or two applications that are actually coming through your caching system. So they've got a view of the data. The other applications have got a different view. So this problem is called consistency or coherency with the system of record. This is an important problem to solve. It can be practically solved in a meaningful way within your application. The absolute poor man's way of solving this problem, which you find in all cases, is the concept of expiry. So expiry is the maximum amount of staleness that you'll tolerate. So it's generally called TTL, or time to live. And that puts a maximum on your inconsistency window with a system of record. But that's a poor man's solution. There's other solutions. There's probably the most clever solution is things like Oracle Database and Oracle Coherence have got this thing called hot cache, where you run off the redo logs, and as changes are made in the database, you can flow those through and invalidate your cache directly. And then you've got all sorts of things in between. So things like ensuring that any of the applications that need a common view of data are actually all going through your cache. There's the ability to read through and write through a cache. So it tends to be very specific to your application what the right answer is with consistency. And then, of course, the other one, which is a little easier to solve and fully within the control of the caching vendor, is consistency with other cache nodes. So if you have a distributed cache, what are the contracts for when you make a change in one? How quickly does that change become visible to others? So the sorts of words that you see thrown around in this area are a strong consistency. So with strong consistency, you're guaranteed that when you're doing your write, that everybody, there's a write lock, so no other nodes would actually see it until you finish. Then everybody then sees the same view of data. Then you can, at the other extreme, you've got weak consistency, where there's actually not even a guarantee that the update will hit the other nodes. So years ago, I wrote a thing called JCache, and JCache had replicated mode. It was actually weakly consistent. It was actually just best efforts. And you say to yourself, well, how can that be useful? Well, the answer is it can be. If you've got reference data, you've got catalog data, it either doesn't change or it doesn't matter if it's slightly out of date. You can be weakly consistent. And then there's the one that tends to be the right answer most of the time, and that's eventual consistency. And that's where there is a guarantee that the other nodes will get it, but it takes some time. Now this is a nice trade-off, because you can make your update without requiring a cluster-wide write lock. The other nodes get it as quickly as they can, The amount of time between an update occurring and all nodes having a common view is called the inconsistency window. Now, most modern in-memory data grids or NoSQL systems, that's measured in microseconds to a few milliseconds. So it tends not to be a problem. But once again, it's the design choice when you're building a system. Most in-memory data grids and caches allow a degree of configurability per cache on which consistency setting you use. Okay, so that was my little roundup of caching. That's my little toolkit, so hopefully some of that will come in handy if you didn't know all those things already. So now, what's been happening in the industry is for a very long time, we've had caches, and they've been very, very highly widely used. So my own effort, JCache, is used by hundreds of thousands of people. It's still, even now, like 12, 13 years on, I'm not maintaining it any longer, but it's still very widely used. You've got a bunch of other in-process caches, and then you've got in-memory data grids. So you've got people like GridGain who are hosting this conference, Hazelcast, the company I'm from, Coherence, Oracle Coherence, Gemfire. You've got these very high-end in-memory data grids, and they've all got proprietary APIs. Now, for a lot of what the in-memory data grids do, that's not a big problem because there is a high cost of change. But for the simpler caching stuff, there's definitely a need to standardize. So the idea here was enterprise Java applications are already using this. We should standardize this area. It standardizes it for Java only, but that's a big step forward. And the design goal was to have the 90 or 95% of the common functionality in the standard. Should be many people that can actually use this and then just swap out to another implementation with only a jar file switch and a config file switch. Let me just do a time check here. So I've been going for about 20 minutes. A couple of interesting points to note was that JCache was developed as part of the Java community process. There's almost no Java specification requests that deal properly with distributed systems. So JCache was one of the first that's actually dealing with all of the intricacies of distributed systems. And we wanted to create a simple API that would work for distributed systems and also not be a burden to implement for simple in-process caches. The goal, which hasn't been realized yet, is to actually eventually end up with one of these actually inside the JDK itself. So a bit of a trip through the recent history. This standard is actually very recent. So the standard itself came out in March 2014. We then had adoption by Spring. So Spring, in the Java enterprise world, Spring is now far more commonly used than Java EE. So they picked it up very, very fast, and it was in September. And they've gone on to do all sorts of interesting things. It's in Spring Boot. It's very nicely and deeply integrated. Hazelcast came out with an implementation, and actually most of the big in-memory data grids actually were done by June last year. Now, what's coming next is an errata release of JCache 1.1. So I've been working on that for some time, and we're very, very close to done. I'll give you some more details later, but that'll be coming out summer 2016. The next thing that'll happen after that is to then broaden the scope of JCache to take on sort of a larger feature set, and we'll get started on that probably at this year's Java 1 after we release 1.1. Oops. So we built this thing to try and standardize what's out there. So for that reason, we actually picked Java 6 as the language level. Now, have we been successful? Well, here are the implementations. I would say yes. So we now have seven certified implementations, and we've got 3 in progress. So We've got the RI, so we have a separate RI that's not production ready. In case you're planning on using it, don't use it. There's JCache. So both JCache 2 and JCache 3 support, which is the most widely used in process cache, support this standard. Hazelcast, Oracle coherence. So Oracle was co-spec lead on the standard. So while we were writing for finishing the standard, Joe Fiorelli was actually implementing incoherence, and that was really invaluable. So we made sure that everything worked properly in a full-blown distributed cache. Infinispan from JBoss, also JBoss Data Grid, which is the commercial form of that. Conference hosts GridGain, so they have it in Apache Ignite, which is the Apache open source project. They also have it in their GridGain commercial, which is the commercial version of Ignite. There's a brand new entrant, a Luckysoft out of Seattle. So they actually have a .NET-based in-memory data grid. So they've actually, it's about 6 months ago, they actually came out with TazeGrid, which is a new Java-based in-memory data grid, implements the spec. Then we got some interesting in-process caches coming out of Europe. I passed over one. So caffeine. So Google have an in-process cache called Guava, which is quite popular. A guy called Ben Maines did most of the work on that. And now Guava does not implement the spec. Google and the JCP don't get on so well, but Ben has left Google and he's got an in-process cache called Caffeine, and it does have a module that implements the spec. A couple of other ones, an Italian company has got a cache called Blazing Cache in process. Actually, sorry, Blazing Cache is distributed, so it's a distributed cache. Cache 2K, a guy called Jens Wilke out of Munich. He's become very active lately and has been helping me a lot with the 1.1 maintenance release. It's kind of quite handy once again because he's implementing the standard and complaining about stuff all over again, and we're having these fresh debates, it's good. So this is going to lead to a high quality maintenance release. And then Trivago, the travel company, hotel booking company, you guys have probably heard of them. They've also got an in-process cache, which is about 90% compliant at this point, called Tcache. So pretty healthy. Now, to keep track of what's going on with implementations, there's the JCP page. Also, Jens Wilke from Cache2K has been helping me out. He actually has a continuous integration of all implementations of JCache. It's that second link there, the Cruftex link up on GitHub. So you can actually see, you see he keeps a very close eye. You can see all of the implementations. So look, the promise is 90-95% most useful subset. You code to that. You start off with maybe an in-process cache like JCache or Caffeine. Then you can go full-blown to a distributed cache without changing your code. That is the promise, and I think we've delivered based on these implementations. So there's no other part of this in-memory space that has got anywhere near this level of standardization at this point. So who's not implementing JCache? Well, our friends down the road at Pivotal. Anybody here from Pivotal? One person. You guys are not implementing. So the reasons that have been given to me is that most people using Gemfire and Geode, which is the open source form of Gemfire, are using it through Spring. Spring already has the cache abstracted, and then when it comes to the annotations that were defined in JCache, Spring did bring those annotations in. So you can use the JCache annotations in Spring, and that's good enough for the Geode and Gemfire community. So that's what I've heard. If you disagree, there's a tag there, Pivotal JCache. Make your comments known to feed them back to Pivotal. I would love for Pivotal, by the way, I would love for Pivotal to implement, then we'd have a clean sweep. No promises. Okay. Now let's look at NoSQL. Can NoSQL implement JCache? The answer is no. So Redis cannot implement. The Couchbase guys tried quite hard. You can't implement. The reason is that JCache is a Java standard, and there's certain things that we do, tricks that we do, that kind of require Java to be present. And it's caching when you get quite hardcore about it. Well, actually, I'll give you an example of what we do. So there's a concept called a cache listener, which observes changes in caches. Now, in a distributed system, and let's take a distributed system where you've got client libraries like JDBC drivers, and then you've got a caching cluster. So you do a put to a cache. That put actually turns out it's an update because there was a previous entry already existing. And then you want to have a cache listener. Now, a very naive way of specifying this would be to say, okay, it's only the client library where we listen. Then everybody could implement. But most of the time, that's not efficient. Most of the time, what you want, and the spec defines it this way, is that an event is only observed once somewhere in the cluster. Now, the most likely place that you would implement it is actually in the cluster itself, not in the client. And to do that, you need to have the Java code sitting in the cluster, not the client. So the cluster needs to be running Java for this to happen. A couple of other things is that to make sure that everybody can do this, what we define in the standard is you provide a factory, a serializable factory for the listener, not the listener instance itself. And that way we can instantiate, it's up to the implementation to instantiate the listener wherever they want to that makes sense to them. So once again, unless you're Java-based throughout, you can't really implement this. Now, the good news is that there's a lot of people that are Java-based, so this is useful. But yeah, you can't do all of these tricks with NoSQL. You could implement a part of JCache, a simpler part of JCache with NoSQL. And one of the things that we're thinking about for EHCache 2 is to actually define what we're calling basic cache. And basic cache would then be able to be implemented by all the NoSQL guys as well. If you're looking to contribute or get involved, it's up on GitHub, JSL 107. There's a Google group for it. It's all up on Maven Central. It's very simple to consume. Let's have a quick walk through the spec. And I'm half an hour in, so I think I'm traveling pretty well. So if you're a programmer or an engineer in the room, you're familiar with a data structure called a map. And human beings have this psychological pattern of anchoring, where the way you understand something new is to compare it to something that you already understand. So that's what we're doing here. Everybody knows what a map is, so I'm going to actually explain JCache by explaining how it's different to a map. So they're both key value based, so they're key value stores. We don't support or define any querying capability in the spec, although most implementations do in fact have query capability. Now map has got concurrent map. Now concurrent map supports atomic updates using the CAS operators. So we also have those. We name them slightly differently, but we have those. Now, I explained before the problem of coherence with a system of record, and that the poor man's solution to that was expiry. So we have to have that. So we have expiry, maps do not. The other thing is that a map's never going to get too big because a map's stuck on heap in your application, and if it got too big, you'd get an out-of-memory error. Now, with caches, only trivial in-process caches live on your heap. Anything else more substantial lives in your off heap, and it might live in your SSD or NVRAM. It might live on disk, or it might be distributed. And the largest Hazelcast cluster is 600 nodes and 7,000 cores, so they can get very, very big. But always there's a maximum amount of resource that you have. And when with the way caches work, you just keep putting stuff into them. You don't have to worry about them filling up because caches will automatically evict. And generally what they'll do is they'll evict based on the least recently used principle. So you throw away the stuff that you haven't used recently and keep the rest. So we have eviction. Now, in a map, entries are always stored on heap, and they're always in object format. Even if it's a byte array, you still hold a reference to that byte array. Now, in JCache, entries, as I just said, they can be stored in any of those tiers. So that makes a huge difference. We can't assume and don't assume that entries are actually on heap. So, and there's a further thing, it's a little intricacy, but in the Java Collections API, if you actually stick in an object into that collection but hold a reference and then mutate the object based on the reference that you held, that changes it for anybody else. Okay, so this is called store by reference. So we defined this term in the spec because it wasn't previously defined. It's just the way stuff works, and everybody knows that who's a Java developer. But it's something of a subtle idiom because you can actually be changing data that other people are looking at. So what we did is we defined store by value. So store by value means anything that's not store by reference. So even if it's on heap and even if it's in object format, when you do a get, you'll do something like a clone or something so that if you then mutate the object that you get a reference to, it doesn't change it for everybody else. It's free for the implementer to do it however they want as long as it meets that guarantee that it's not store by reference. Now the default in JCache is store by value, but it's a configuration switch because most of the time within process caches, you want to run store by reference because it's way faster. There's no extra work to do. Now the JCache has got an integration package because we know that we're holding a copy and that the system of record or true copy is somewhere else. We know that this situation usually exists. So we have an integration package and we facilitate built in the concept of being able to hit the cache and if it's not present, have the cache through a class that you provide, load the missing data. That's called read through. So we support that and the interface is called cache loader. The other thing that we support is you write to the cache and then you want the cache to write to the system of record. This is one of the mechanics for resolving the coherency with the system of record problem. So that's called write through. So that's a cache writer. So we define cache loader and cache writer. Now it's not defined in the spec, but of course another interesting thing that people do in busy production systems is they batch their writes. This is a great way to take write load off a database, and that's called write behind. We know about it, we didn't define it in the spec, but most implementations of JCache support write behind. I talked about listeners before. Now I talked before about cache efficiency. You know, it's possible to stick a whole lot of data in a cache that's not doing any good. You've got to be, the concepts are a little bit subtle, and you've got to be very careful about data correctness. And you've got to make sure you're doing some good. So we have statistics built into the spec. And lastly, there's a really, really important primitive from in-memory data grids. And we wanted to make sure, this is the most important thing in in-memory data grids. We wanted to make sure that we actually properly got that, and that was entry processes. I'm going to talk about those in a minute. So I think I've covered most of these things. One thing, and I've got a slide on it, is annotations. So the ability to take take methods and with an at cacheable, just make it cacheable that way, makes it very easy to use. Supported by Spring, as I said, since 2014, 4.1. I think I've covered this, but just to be really clear, that we support the full range of topologies. So in process, distributed. Now a quick walk through the key classes and interfaces. So we have this, and I'm going to use the database metaphor here, back to the anchoring thing. You have a so in a database, you have a database instance. The database instance has got tables. So, and you might be, you're running a particular type of database. So let's say you're running Oracle. That's your database provider. We have caching providers. You can have multiple caching providers in your class path, and there's a way of firing up a cache manager from a given provider. So you can have 3 or 4 all there. Then you have a database, and the equivalent in JCache is a cache manager. And it creates and manages caches. And then you have a cache, and a cache is like a table in a database. And then below that, in a database, you have rows. In a key value store, you have keys and values. So that's called a cache entry. And then we have a form of that that you can mutate, which is called a mutable cache entry. This is what the code looks like. Caching, we have a utility class called caching. So caching.getCacheManager. If there's only one instance on the class path, it'll provide it on the class path, it'll just grab it and give it to you. And then you look up a cache. Most of the time, you're connecting to caches that already exist. And then you do cache.put, cache.get. So this is a very, very simple API, but the concepts are actually quite subtle. I'll skip over the IDE, and let's just make a few comments about entry processes. So with an entry processor, you have user code which is installed on your grid, and then you can give a key and some arguments, and it's basically a command pattern. You say, for this key and these arguments, I want you to do something, and I want you to use this command. So the entry processor is like a command. It's the old command pattern. So this is an increment processor. This shows how you'd code that. Now, the beauty of this and why it's so important, and we put it in the spec, is that what it avoids is cache.get, do some stuff, cache.put. So you're skipping the payload going over the network twice. And the other thing is, what happens if you want to lock? What if you're in Oracle database? You can do select for update. You're going to change something. What if you want to actually lock that so nobody else can read it or write to it while you're doing it? So then, do we add a locking API? I used to be CTO at Terracotta. We actually had a locking API for doing this. So the beauty of this is that if you have a lock-based API, you'd have to do all those steps down there. Now, when you do cache.lock, network trip, cache.unlock, network trip, put, get, put, all network trips. You can do this in one single network call, and the data does not move. It's processed in situ without moving. So you can blow performance through the roof using this approach. So we actually added it to the standard. Annotations, they're the annotations. So get, put, remove all. Very easy to use. There's an example. Spring. So I'm whizzing through these because I'm out of time. How much time do I have left? 7 minutes. So leave some time for questions. You'll have the deck. You can look at these links. EE is a bit of a weeping sore that never heals. So we were too late for EE7. And then EE8 itself just seems to have trouble getting started and getting going. So we're ready if they are. I've tried. There's a group that's been trying to get these guys going. I've said, let's get going. I don't know if it's ever going to get implemented, frankly, in EE8. And I'm not even sure if it matters because you can actually use this anyway with EE. This is a spec that only relies on the JDK. You stick it in your class path and you can interact with it. So the main thing, I guess, that would be added through EE integration, the main thing would be annotations, annotation support. But it's only one way to use the spec. The spec's still very useful without it. Adam Bean is leading the effort there, and there's a link where you can get involved. Let's have a quick look at the future, what's coming next. We discovered that one of the big problems that we had with JCache is that Brian and I, being first-timers to this, we used the JCP license, which is not an open source license on the spec. We had no idea that you did anything different. And it turns out that what people do is they use generally a CDDL license on the header and in the API that's distributed as code, and they use a spec license on the spec. So this is something we're changing in 1.1. I don't know what it is, but every time we do something, it feels like we're doing it. It's being done for the first time. So Brian Oliver, who's my counterpart at Oracle, he's been talking to the lawyers there, and the JCP process really isn't clear on this point. There's no mention of this practice. And when Brian spoke to the lawyers, Oracle wasn't even sure what this means. It's like, what does that mean? It says open source on the API, but actually the spec document doesn't. There's a conflict there. So it's a bit of a mess. So we'll have that. There's a bunch of errata, nothing too serious. It was a pretty good 1.0. There's TCK challenges, so we've got 10 implementations, right? So when somebody implements, they actually challenge something and they say, oh, I don't think this is right. So we have a bunch of those. But all in all, I guess across the spec, maybe there's been something like 20 issues, which are very, very minor in nature. So we're very, very close to finishing this. I did some work on this a couple of weekends ago in Munich with Jens. I think that we'll probably have this done in the next few weeks, and then by the time we get it out, it'll be summer 2016. So that'll be nice. We'll probably do a talk at Java 1 to talk about it, and then move on and actually open up, I guess, what a lot of people are more interested in. The maintenance stuff's boring, but it's 2.0. This is kind of what we've got in mind so far. We dropped transactions. Transactions are probably only, I don't know, 2 or 3% of caches, I guess, that I've seen use transactions. So once again, when I was talking about 95%, you know, this was something hard to add to the spec that we dropped out. We do have a chapter that we can resurrect from the spec, but this will be XA transactions. Obviously, they're not fast, but sometimes they're important to use. I guess working with the EE guys, it looks like to get into EE8, we would need to lift our Java version to Java 8, and then we would, I guess, have to do some work on the annotations integration. Servlet integration, I mean, pretty much every cache out there is integrated for web session clustering. So this is like an obvious thing that we should look to do. There are enterprise features over to the core. Brian wants to prepare for Java 9 modularity. I'd like to add an async API. We pretty much all have async APIs, and with reactive, that's really important. It's a detail that's missing from the cache. Another one that's less likely but interesting, Java util stream is designed as an in-process approach. We're implementing distributed Java util stream. A couple of the other IMDGs have, and there's a bunch of other folks that are as well. There's no standard in this space, and it's crying out for it. So I was trying to get this guy that gave a talk at Java 1 2 years ago and raised a JEP to do this. If not, maybe we extend JCache into this area. And then the idea of actually having a basic profile to allow the NoSQL guys to implement, and we'd be dropping, from that basic profile, we'd drop listeners, integration, and entry processor. Hazelcast, great implementation of JCache. And I guess with that, I'm going to open it up for questions.
I have a question about cache correlation. So I have a distributed Cassandra cluster that I'm writing to, and I'm reading from one end, writing to the other end. How would I invalidate a cache on the read cluster from a write? So the write happens in one data center. It's replicated to the read-only data center. And now I have application servers hitting that read-only.
This is in Cassandra? Okay, so this is just a general caching question rather than a JCache question?
No, so I have application servers connected to a Cassandra cluster, and I have a cache in between.
Okay.
And now somewhere over here, some data gets up.
Okay. All right. So the question is how do I handle consistency when I've got WAN and I've got 2 data centers? In addition to that, I'm actually using write through and read through to Cassandra. So this is actually quite a common situation. So the answer that the industry has so far is that no one attempts anything other than eventual consistency across the WAN. No product that I know of that actually tries to do anything different because the latencies are just too high. You've got hundreds of milliseconds, so it would just crush performance to do that. And that's how we work. So most people's WANs are push-based, eventually consistent. So now, so if you were writing to a cache and the caches themselves were distributed with then WAN integration between them, what would happen is you write to the cache will within a number of milliseconds to seconds update or invalidate the entry. In our case, it's actually would update the entry in the other WAN cluster. Now you're doing it with Cassandra. I guess with Cassandra you can have Cassandra that spans multi-data centers. Is that how you've got it set up? Right, so Cassandra's kind of the eventual consistency of Cassandra is taken care of, but what's not taken care of at the moment is you've got 2 caches that do not become eventually consistent. They will eventually through TTL, or through TTL is the only way. So the answer is what you need to do is you need to set up WAN integration between your two caches, which Hazelcast does and most of the caching vendors do.
So I saw in the last slide something about a listener in the NoSQL data store. Would that sort of negate the necessity?
No. You have a problem with the consistency of your two caches in each data center. That's what you have today, and there's the solution to shorten that inconsistency window would be to eventually set up replication so that you're eventually consistent within a couple of seconds.
Do I not need a cache on the right side since it's not serving traffic? Would there be a way to do it without that?
Yeah, well, if you're only writing from one data center, yeah, just remove the cache over there. Yeah, sorry, missed that part. All right, I'm out of time, so I'm going to go and stand just outside the door. Just come down and see me, okay? It's only a 5-minute gap and then another talk, so I'll be standing down the back, and then if you miss me there, I will be at the Hazelcast booth, okay? Thanks for your attention.